Hello. This is an open title scene for this template to use at the beginning of your video. Simply edit the text with your details. A convolutional operation, often used in the context of convolutional neural networks, CNNs, for image processing, can be thought of as a moving filter applied to an image. Imagine you have a digital photograph, which is really just a grid of numbers representing different colors. Now, suppose you have a smaller grid, let's call it a filter or kernel, also filled with numbers. This filter might be very small, perhaps 3 by 3 cells, compared to the image. The convolutional operation involves taking this small filter and sliding it over the image, 1 pixel at a time. At each position, the filter covers a small part of the image. We then multiply each number in the filter by the number in the image cell it's covering, and add up all these multiplied numbers. The result is a single number that represents that specific part of the image. This process is repeated for every position the filter can move to on the image. The result is a new grid of numbers, often called a feature map or convolved feature, which is a kind of condensed representation of the original image. The beauty of this operation is that the filter can be designed, or learned, to recognize specific features in the image, like edges, shapes, or textures. By using many different filters, a convolutional neural network can learn to recognize many different features, and combinations of features, in an image. This is a key part of how these networks learn to understand and classify images. Convolutional operations are particularly important in image data for a few key reasons. Feature learning. Convolutional operations help in learning image features automatically and adaptively. These features can be simple edges, shapes, or more complex structures like objects. The filters adjust themselves to extract the most useful information for the task at hand, such as recognizing faces or objects in images. Translation invariance. Once a feature is learned, a convolutional operation can recognize it anywhere in the image. This is because the same filter is slid across the entire image, allowing it to detect the feature regardless of its position in the image. This property is known as translation invariance, which is particularly important in image recognition tasks where the object of interest can be in different locations. Reducing computational complexity. Convolutional operations reduce the number of parameters to learn, compared to fully connected networks, making the network easier to train. This is because each filter is relatively small, and the same set of filter values is used for every position in the image. This sharing of parameters greatly reduces the computational complexity of the model. Preserving spatial relationships. Convolutional operations take into account the spatial relationships between pixels in an image. This is crucial for many tasks where the arrangement of the pixels is meaningful. For example, in an image, pixels close to each other are often related in the sense that they are part of the same object. In summary, convolutional operations are a key component of convolutional neural networks, CNNs, which have been very successful in tasks involving image and video processing. The conv1d layer, or one-dimensional convolutional layer, is a layer used in neural networks for processing data that has a temporal or sequential nature. While conv2d layers are used for image data, which is two-dimensional, height and width, conv1d layers are used for data that is one-dimensional, such as a time series or a sentence. Imagine you're looking at a sentence, one word at a time. You start with the first word, then move to the second, then the third, and so on. A conv1d layer works in a similar way. It uses filters that slide across the one-dimensional data, looking at a few words, or data points, at a time. Each filter in the conv1d layer is like a tiny detective. It's looking for a specific pattern in the part of the data it's currently examining. When it finds this pattern, it produces a high output. By sliding the filter across the entire data, the conv1d layer can detect the pattern anywhere in the data. This makes conv1d layers very useful for tasks like natural language processing, where the data is a sequence of words, or time series analysis, where the data is a sequence of measurements taken over time. They can learn to recognize important patterns in the data, which can then be used for tasks like classification, prediction, and more. conv1d layers are particularly useful for time series data due to their ability to handle sequential data effectively. Time series data is sequential in nature, with each data point related to those before and after it in time. This is similar to how a sentence is a sequence of words, where the order of words matters. Here's why conv1d layers work well for time series data. Temporal patterns. conv1d layers can learn to recognize important temporal patterns in the data. For example, it might learn that a sudden increase in a stock's price followed by a gradual decrease is an important pattern to recognize. Translation invariance. Just like in image processing, once a conv1d layer has learned a pattern, it can recognize that pattern no matter where it occurs in the time series. This is because the same filters are applied across the entire length of the data. Local focus. Each filter in a conv1d layer focuses on a small, fixed-size window of the data, which can be slid across the entire time series. This allows the model to focus on local patterns, where a specific set of data points are related to each other because they occur close together in time. Efficiency. conv1d layers are computationally efficient, especially when dealing with long sequences. They reduce the number of parameters to learn, making the network easier to train. In summary, conv1d layers are a powerful tool for analyzing time series data, capable of learning complex temporal patterns and relationships. This code is creating a model to analyze sequential data, like a series of measurements taken over time. It's using TensorFlow, a powerful tool for machine learning, to build this model. The model is made up of a sequence of layers, each performing a specific task. The data will pass through these layers in order, with each layer transforming the data in some way. The first layer is a conv1d layer. This layer is like a tiny detective, looking for specific patterns in the data. It uses 32 different filters, each looking for a different pattern. The kernel_size parameter tells each filter how much of the data to look at once. In this case, it's looking at conv1d number of data points at a time. The relu activation function is used to decide what information should pass forward to the next layer. The second layer is a dense layer with 32 units, which means it has 32 neurons. This layer is fully connected, which means each neuron takes input from all neurons in the previous layer. Each neuron applies the relu activation function to its input before passing it on. This layer can learn to recognize more complex patterns based on the output of the conv1d layer. The final layer is another dense layer, but this one only has one unit. This is the output layer of the model. It takes the high-level representations learned by the previous layers and turns them into a final prediction. In essence, this code is creating a neural network with a conv1d layer and two dense layers. This network would be capable of learning complex patterns in sequential data, making it useful for tasks like time series analysis or natural language processing.